Okay, hello everybody. Welcome to the sixth lecture. So previously, last week, we examined a simple example of stochastic evolution, right? We took a qubit system and coupled it. Let me scroll up. Right, we took a qubit system and we coupled sigma z operator to a random telegraph noise. And because this Hamiltonian has this very simple form, we found out that we didn't need time ordering to handle the stochastic map generated by this Hamiltonian. And on top of that, we find out that we actually can diagonalize the generator, and thus we could proceed very far with analytical calculations. And we found that the stochastic map can be calculated and has this diagonal form where everything is governed by what we call the coherence function, which is essentially a averaged exponent of integrated stochastic process driving the system, and its action on the initial state can be easily computed. And as you can see here, it's like only the off-diagonal elements of the density matrix are affected in this simple scenario. And on top of that, because we use a random telegraph noise as a example in our model, random telegraph noise actually allows us to calculate analytically this average here, and you get certain formula which boils down to the fact that for long times it gives you a strong exponential decay. Okay, which means for our dynamics that the off-diagonal elements are dumped over time with exponential decay, which leads to the this kind of effect where you erode the of things of the diagonal of the density matrix, and which means, by the way, that the stochastic maps, stochastic dynamics does not preserve purity of the state. Right? You can start with a pure state at time zero, and proszę. Zacząłem już mówić do wirtualnej widowni. Okay. So I was just summarizing the previous lecture, so you missed nothing.
Okay.
I just said that we examined this simple model of qubit coupled to random telegraph noise, and because it was very simple kind of evolution, every time ordering wasn't needed, right? We could diagonalize everything, and we end up with this evolution of this form, right, where the off-diagonal elements of the density matrix is multiplied by this coherence function, as I called it, which for telegraph noise exhibit this asymptotic behavior where it just dumps exponentially everything, which means that over time, right, we just get rid of the off-diagonal stuff, which means that you can start with pure state, for example, and over time you get to a mixed state, which is a new feature. And before we go further, I want to point out that this kind of dynamics can be generalized to something that's called in the business pure dephasing dynamics. So pure dephasing, you get pure dephasing when you have when your Hamiltonian, your stochastic Hamiltonian. Where is my cursor? Here it is. Okay. When your stochastic Hamiltonian of T have this kind of form, some coupling constant, the stochastic process of any variety, and some operator V. Okay, which operator V we can always write its spectral decomposition, right? So this would be eigenvalues, right? And this would be eigenstates. So in other words, we can make a basis out of eigenstates of V, eigenkets of V, and right, this is a eigenvalue of V, which means that when V acts on ket N, it spits out a number times ket N. All right, so this kind of Hamiltonian, it should be clear that it commutes with itself at different points in time, because this is just a constant operator V multiplied by number, right, by stochastic process. So these guys commute. So time ordering is unnecessary here. So the dynamical map, sorry, the stochastic map for this kind of generator is, again, is just exp minus lambda. You have to integrate the process F, and you have generator and average. And the generator is constant and is a adjoint of V, right? Right. The time ordering is unnecessary because V is constant, right? And moreover, it wasn't an accident previously in our previous example that when we took a basis in the space of operators made out of cats and brass of sigma Z, right? And it turns out miraculously that this basis was a correct basis because the super operator was diagonal in this basis, if you recall, right? That we didn't have to diagonalize anything; it was diagonal for free, and that wasn't an accident actually, because if we now take a basis made out of cats and brass, projectors and coherences, let's call it, made out of eigencats of V. This is also gives us that basis in which this V is diagonal, and this is simply because these operators here are eigenoperators of this super operator, right? Like you have operator that has eigenvectors, super operators has eigenvectors or eigenoperators as well. And it's very easy to check because we take V and act on any one of those guys. I can just compute it explicitly. So we take a commutator, right? So this is V acting on N, M minus N, M, V. Okay, but that's easily calculated because those cats are eigenvectors. So we get this minus Vm and M, right? Which means we can extract the common factor.
Why the second step? This first step and commutator?
That's, give me a sec. V, this guy is a adjoint of Hamiltonian, okay. Right? So its explicit form is, so you put it in and act on the operator. So you just gobble it up, right? And you get a number times the operator, which means it's an eigenoperator. And note here that this eigenvalue is not zero
So why in this commutator you have bra n instead of m?
Because I made a mistake. It's a simple answer this time.
Yeah, in the notebook also it's very easy to make a mistake. Like I sometimes look at my notes, and when I'm writing very fast, it's very difficult.
Yeah, everything is n, m, or, or yeah. Okay, so this is a simple calculation. In case of qubit, right, for sigma z, it was the same stuff, just two-dimensional, so very simple to calculate. So this means that it's trivial to diagonalize the stochastic map, and it's very trivial to actually figure out how it acts on the initial state, which can be summarized. So, wrong button, sorry. So we take ut act on some row 0, and let's take a matrix element, right? Because this is density matrix, we act on it with stochastic map. So it spits out row at time t, right? So density matrix. So an operator, so we can take a matrix element of it. And if because for when n equals m, the eigenvalue is 0, right? Those will be, it's easy to calculate. So the diagonal, the diagonal elements of the density matrix will remain constant, so nothing changes for them. So just like with qubit. And for the off-diagonal guys, because in this case the stochastic map activates, you will get similar effect. You get some factor multiplying the diagonal elements. Okay. And this W is coherence function. Now with indices, it's exponent minus I lambda, and the eigenvalue integral of process ds, and everything, of course, has to be averaged. Right? And because whether you can calculate the average depends on the process f. Typically, you cannot do it analytically. We get to that soon. And so this kind of evolution, where the only thing that changes in time is this kind of characteristic function, coherence function. You can call it many names, but it's like the average exponent of integrated process. This is what we call a pure dephasing dynamics, and the name comes from the following observation that you can if I write down this kind of, let me just put here like universal constant. This this constant depends on n and m, but it's the form is like you have a process integrated times constant, and you take x, and you can like think of it as a average of a phase, of a stochastic phase, so average phase factor. So with the phase, it's like minus I, no, not I, minus G and integrated process, right? So this is like you take a phase, which the complex phase, you can always like think plot it on the complex plane, right? It would be like a unit, like a vector pointing on some place on a unit circle, right? So this would be like imaginary real part. So you have this kind of phase, and you average over realizations of this stochastic phase. Let me see. And now you can, this average, you can always think of this average as a, like you take limit, n goes to infinity, 1 over n, and you take an arithmetic average over samples, okay? From 1 to n, to sample, okay? And so the intuition is that this kind of average of phases will tend to 0 for large enough phases, okay? And the reasoning is that, when you let time go on, right, this integral will just accumulate. And this, as phi gets longer and longer, you can see that it will start to wobble around this unit circle, right? And you let it accumulate more and more and more, so it will start to travel more and more, wiggle around, stuff like that. And after some time, when it's long enough, it will just travel the whole circle to pi, and maybe it will wind like that many times. And after that, you have like your samples become like really randomized, right? You have like bunch of those unit vectors pointing in all the directions, essentially. So when your phases are long and you have a large enough number of samples, you can, like, for every one pointing in certain direction, you will always be able to find the counter phase, right? Something that points roughly the opposite direction, canceling with the first one. So you can like see that as you wait, your samples spread over this circle, and everything starts to cancel each other. And this is like this intuition where the phases start to dephase. They start from 1 pointing in at time 0, they point in unity, and then they start to spread and cancel each other. So this is this intuition, mathematical proof that it works like that. I haven't seen a really nice calculation, but this is, for random telegraph noise, you saw the exponential damping, right? So this is like a more or less universal behavior. So that's why this kind of evolution, because it's governed by this average over phases, is called pure dephasing.
So what would be the idea how to prove it?
I don't really know. I try to, typically when people see this, they just skip and they say, oh, it's clear that, it will just kill, the sum will just go to 0. Even in Feynman lectures of physics, there's a chapter where he does this kind of thing, and like the plots of arrows and stuff like that. But to see a concrete calculation, I haven't figured it out yet. I don't know what is the good proof of that. Simple and accurate. There is some way to show that it will start to drop as 1 over square root of n, the average, the number of samples, but it's I don't know. But this is like strong belief. People believe that it works. You see this kind of sum. Oh, it's just 0.
It's like with the Gaussian distribution, maybe. Oh.
That's if you have some specific distribution of those phi's, right? You can do a lot. You can calculate quite a bit, because this is like you will get some kind of Fourier transform here. So it's not that difficult. But the idea is to show that it's a kind of universal behavior, to figure out what are the, what's really the ingredient, the secret ingredient that's needed there. And I haven't seen this. I don't know exactly. because that, you would have to capture this effect that the phases have to accumulate over time. The integrals have to, this thing has to be so that they are like start to wind around, and then it winds many times. They start to decorrelate, randomize completely, and because when there is some structure, when the way they don't randomize enough, you will get some trend, right? And this won't go to zero because they will like cluster around some angles. But the idea is that it should like spread uniformly, more or less. And how to show it, I don't know. I mean, maybe now I would be able to figure it out because I haven't looked at it for a couple of years. Maybe someday. Oh, maybe you will come up with something. I mean, it's a nice exercise. I would love to see it.
Nice, like to see that, but it's like obvious that it
Yeah. The pictures are clear, right?
Yes.
It's even, so obvious that it has a name, the phasing. It's like, yeah. All right, so that's this like we will use it in a bit, this name and this stuff. So now one more thing I thought about talking about just to finish this, but I changed my mind. So I pointed out that for qubit that we had this effect that you get mixed state. You can start with pure, you get mixed state. So I planned to like formalize it a little bit more, but I think it will be waste of time right now to talk about it. So you can treat checking out section 3.5 as a assignment, home assignment. It's a short and sweet section, talks about entropy of states as a measure of mixedness or purity, whichever you wish, and like discusses some simple theorems. So check it out for your own curiosity. Okay, which screen I'm sharing? Good. Yeah. Okay. So with that out of the way, we can get to the real stuff. Now the talking begin. Okay. So we get to the next big point. So we have some idea about stochastic maps. We've seen examples, simple examples, but we saw some things. We touched a bit and practiced a bit with stochastic processes. Random telegraph noise is a nice example, but now it's a real problem or real issue is 3.6, right? The question of computability. Computability of stochastic maps, right? Because at the end of the day, you probably have to calculate something at the, to proceed further. So the question is, how often can you actually calculate anything? And the first subsection is kind of grim because there is no dynamical equation for free. So this is like a bad news. So when we considered computability of unitary maps, right? The main issue was time ordering, right? Because this is like you can write it formally, but actually do the calculations is unfeasible in most cases. So how to deal with this? Oh, you have dynamical equation. If you're something you can integrate to iteratively numerically compute the map, and it's like it's doable in most cases, unless some dimension is very large, then you have to do some tricks. But standard approaches, standard numerics usually allows you to defeat time ordering in this sense. So in case of stochastic maps, we still have to deal in general case with time ordering, but there is also another thing, the average. You have to compute the time ordered exponent, but then you have to average everything. There are two problems. So the question is dynamical equation method so powerful that will not only will allow us to deal with time ordering, but also the average. Let's check. So how to check if we have a dynamical equation? Well, you take your map and you calculate derivative, right? So we take a map, some V, okay. So we take some generic map. We have a process, and we have some interaction picture generator, and we take average, and we want to take the derivative over time. And just to as a reminder, maybe because we haven't seen those guys in a bit, Vs is a adjoint to interaction picture of V hat, right? And V hat was IH0S VH0S. Okay, if you go back a couple of lectures, you will there was a bit about this. All right, so yeah, derivative. Okay, so with derivative we can enter under the sign of average. There is no problem with that. ds v s s. So everything is under the average together with the derivative. But we have time ordered exponent. We know how to calculate derivatives of this guy. You know what? If I may, no, I won't. I was tempted to erase the stuff, but I want to erase it. So let me step here. So you do the derivative, you will get minus I lambda V t f t and the exponent minus I lambda 0 t f s v s and the average. Where is average? Well, average is like this. So hopefully you can see that it, right? Vt is not stochastic, so it's not affected by the average. So we could pull it in front, but the f that was spilled out, it's caught by the average because it is stochastic. In other words, the thing we got here, this is not the same as this, right? It's not just time ordered exponent averaged. It's f times time ordered exponent averaged. So we did not. This did not reconstitute itself into the stochastic map on the right-hand side, which means it's not a dynamical equation. It's not of this form. Right-hand side is like something that's somehow related to the thing on the left-hand side, but it's convolved with some other stuff. And so this is a problem. This is why we don't have no dynamical equation for free. Okay, this average is a problem here. And to actually clarify more precisely what is the nature of this problem, because we have two things here. We have the average and we have the time ordering. Both are hindering us here. Okay, so let's to focus on the problem with average, with the stochastic part. Let's switch for a bit to the simpler scenario where we have a pure dephasing kind of dynamics. Okay, so the case when time ordering is not needed, but the whole evolution is just governed by some kind of coherence function, something that looks more or less like this. Right, and average. So pure dephasing. So pure dephasing. So if in pure dephasing, this is the only thing, the thing of this form is the only thing that changes in time. So the question of dynamical equation then is, okay, what is the derivative of W, of the shape of W? And again, if we just calculate the derivative here, we will get the similar result as before, but we are unburdened by the addition of time ordering. So we can focus on the new problem. Right? And we can even expand the exponents into a series just to be super clear what's going on here. Oh, I had this convention that W had plus here. Let's stick to that convention. Less minuses, less space to occupy. So if I expand the exponent, I will just get the following series. I lambda n plus 1 divided by n factorial. Here we don't have to bother with ordering the integrals, right? Because everything is just numbers, and we have moments, but fancier moments than usual, right? And this guy is a problem. This additional guy, which comes from this, the f that's spilled out in front, because this is not the W does not reconstitute itself on the right hand side. So if you look at this, what kind of solution would satisfy us? Okay, what would have to happen to actually get something like dynamical equation? Well, if those moments here had some kind of fractal structure, let's say, right? So you get your moments, but they can be like factorized in some pattern, some nice pattern, so that you could stick out the factor that contains this extra f. Then maybe we will be able to factor out the common factor, and the rest of the series would reconstitute itself in W in some way. So this is what I'm talking about here is something similar to what happened for random telegraph noise. If you checked out the one of the assignments, so let me just pop here, because for random telegraph noise, the W could be calculated. This thing could be calculated, and we did it in the notes by solving a differential equation for it, right? Because we made here an observation that when you differentiate W, right, it's the R, additional R splits out, but the moments of random telegraph noise have this kind of fractal structure. So there was like W reconstitute itself actually on the right-hand side, but it's not good enough because this is like, it's not a time local dynamical equation. It's time non-local because the W on the right-hand side is under integral. So this is not dynamical equation. With telegraph noise, we figure out we can cope with doing additional more derivatives, right? But we want to get something that's like this, but local in time. Okay. So the idea would be to find out or force some kind of fractal structure on moments. Okay. This factorization pattern. So that would be the idea that we want to pursue. And to pursue this idea, there is a way. There is a formal way of talking about this factorization pattern and this fractal structure. And this thing is called 3.6.2, a cumulant expansion. Okay, so this one is big. So maybe you can take a 5 minutes break because it's like let's take 5 minutes break, okay? And but I think 5 minutes are up. So yeah, let's continue. So cumulants is one of my favorite things actually. There are many things I like, my cats, for example, but the cumulants are like not a distant third or fourth after cats. Yeah, so cumulants. So to introduce them, you have to make this a little bit weird thing. So next page. So let's consider. Okay, so I'll give you a second. Consider. Let's wait a minute for the. He got a phone call, so let's wait a minute. It's so good. All right, so let's consider a following implicit definition. Okay, so we write on left-hand side, we take our, say, coherence function. Fs and the average over it. So this is a coherence function. And we want to make it equal to the following guy. Exp. We write it like this. There is a sum here. Goes from 1 to infinity. I lambda power n factorial. You had integral. Multiple integral. And here are the things we want to define. And this would look like a moment, but you got another bar here. Okay. This is an implicit definition of those guys here. Okay. So this is what's called cumulant. it's a, the notation is like, so it looks like you take some kind of fancy average of the product of f's, because in the end, it will turn out that it is something like that. So that's why this kind of notation. So this would be a implicit definition of those guys. So we have infinite family of cumulants of, first order when there is only one f, second order two, and so on and so forth. And the exp here, just to give a name to this guy, this we'll call it a cumulant series. Cumulant series. So we have moment series, cumulant series, right? And I will call it, I would give it a symbol high. Just to make it super extra clear. Integral. And cumulants. This one. Right, so high is a cumulant series of process F, okay? And it's made out of, is a sum of cumulants of process F, infinite number of them. So this is an implicit definition, but is it a good definition? I mean, what it actually tells us? Well, to get an explicit expressions for cumulants, the procedure is quite simple. You just expand left-hand side into a series, and you expand the right-hand side into a series, and you compare the terms of equal order in lambda, in the parameter lambda, on left-hand side and right-hand side, right? And this is how you can go from the lowest order and progress, and in this way you can you can nail down successive orders of cumulants in terms of moments of F. So let me show you examples. So when you do this, so we expand this, and start to comparing from lambda to the power 0, so the lowest order, to lambda power 1, so on and so forth.
What is this double line operation?
For now, you can, at the moment, you can think of it as this is just a big fancy symbol. This is like complicated, instead of using one letter with some indices, we're using this weird compounded symbol. And the reason is because it actually, in the end, we will find out that it actually behaves like you take a product and taking some weird kind of average, okay? So that's why this, so the notation is supposed to mirror the notation for moments, okay? Because the behavior is similar. They are moments and cumulants are intrinsically connected with each other. So let me write a couple of examples. So expand this, and start comparing the orders, and you get the following. So for lambda 1 order, you will get that the cumulant of the first order actually equals the first moment. Okay. Do you want to see this in action, actually, this expansion? Okay, so let's do it. I was thinking about maybe letting you do it on your, maybe some kind of assignment, but no, let's calculate. So left-hand side. So left-hand side. So we would get, so someone molests me with phone call. TFS. Left-hand side is simple, right? This is the easy part. So we get lambda 0 order. So let's write it like this. It's just 1, okay? Plus I lambda power 1. So the first order And so this is like first moment. Then you get I squared lambda squared 2 factorial. You have double integral S1 fs2 fs1 moment, okay, and so on. The rest you can imagine what's going on here. So we have 0, first, and second explicitly written down. Okay, so what happens on the right-hand side? So right-hand side is an exp of a series, right? So it's, oh, that's kind of weird. So you have to go in steps, right? It's 1, 0, 2, and you have our cumulants. And so if you like just optically examine the two formulas, you see this is like exponent of everything averaged, and this looks like oh, we like sucking in the average into the exp itself. Right? This is like the idea what we're trying to do. If average exp, and you want to have exp of average, but it's not for free, right? The stuff changes, and this changes that the average changes into cumulant average, let's say. Yeah, but let's start to expand this. So how do you proceed? Well, you have this exp here, right? So the zero order is 1, okay, for sure. That's lambda 0 plus, well, the first thing. So 1 over 1 factorial and the whole series or cumulant series plops down, right? So you see, it already have the first term in the expansion of the exponent already has all the terms from the cumulant series in it, right? So you can see that there will be some shenanigans here, but it's not super complicated once you get used to it. So remember, this thing is, I called it high f of t, right? So the second order, so 1 over factorial 2, and you have high f t squared, right? So twice the series, and so on. Okay, so you can see that there will be some. So we have 0 order term here. The next guy it doesn't have a 0 order term because the sum starts from n equals 1. Okay, so we start with first power of lambda at least. This term, it starts with lambda square at least, right? So let's start to chisel it out. So we have lambda 0 is still 1, nothing changes here. So let's collect lambda to power 1. So like I said, this guy starts from lambda squared, the next guy starts from lambda to power third, and so on. So lambda first order is only from the first series, from first high. And it's actually, when you look what's going on here, it will be I times lambda to power 1. There will be a single integral and cumulant of order 1. All right. So second order, what we get? So 1, the second term from the first series is proportional to lambda squared, so it comes in. So we will get I squared factorial 2 and double integral to ts1 s2 fs1. Okay, so that's all lambda squared from the first series, but the second one also has lambda squared term. So we have to account for it as well. But that's easy enough to do. So we will have I lambda power 1 over factorial 0 t f s1 ds1 cumulant times I lambda 1 1 0 t f s2 ds2. Okay, and the other stuff is lambda to the power third or higher. Right, so this is square 1 1, and now we compare the two. Okay, zero order is the same, so nothing new is learned. First order, we get it's an integral of a moment, I times integral of the moment, and here we have I times integral of cumulant. So this is how we find this. Okay. Now you go to the second lambda square. So you have a second cumulant, and you have a product of first cumulants, which we already know what they are. They are moments, right? So you can just substitute here. You can substitute here fs2, fs1, right? So you get that minus second cumulant minus product of first moment times first moment, okay? That's on the right-hand side. So we will get lambda squared would be fs2, fs1 cumulant plus fs1 moment times fs2 moment, and the integrals and the factorials. So 1/2 here, additional 1/2 here. And on the right-hand side, you have a second moment here, okay? Divided by 2 times -1 and the double integrals. Okay, so once everything is said and done, I knew I'm forgetting about something. There is 1/2, additional 1/2 here. So all this is multiplied by 1/2. So there's 1/2 here as well. Good. I was missing this 1/2. Oh my God, will I show you that everything is wrong? No, fortunately it's not. So this gives us the answer that second cumulant is 1 equals second moment minus this additional stuff. So minus the product of first moments, of averages. We actually called this stuff previously as a correlation function. I believe this was the notation I chose for it. So this was like a dispersion. So you had for stochastic variables, you had an average and a dispersion, or not standard dispersion, whatever. And for processes, you had average and the correlation function. That's like the analog of the dispersion. So this dispersion correlation function is the second cumulant, actually. And this pattern reproduces itself. You get then you go to third order. You can use what you got in first and second order to eliminate some of the terms, and this will allow you to successfully express the third cumulant through moments of third moment, second moment, and first moments, and so on. The pattern is getting more and more complicated as you go down the ladder or up the ladder, depending on your point of view. But it's always you can always proceed forward. Okay, you will never stop. There won't be a unsolvable equation and stuff like that. This implicit definition thus is well formed, because it actually gives you a procedure for to getting explicit expression for every cumulant up to arbitrary order, whatever you want. This is always works. Okay, so this is a well-defined. Cumulants are well-defined quantities, in other words. So I won't be writing down the third cumulant because it's too big, and so hopefully this kind of explains how it looks. In practice, we will be using mostly first cumulant, which is the same as average. So it's boring, nothing fancy here. And like second cumulant is our workhorse. Okay, going beyond that, it's rare in applications. Okay, but it's good to know, to be sure that you can go as far as you need. But this correlation function or second cumulant, this guy is the thing. Okay, this is the thing. This is the important bit. All right, so that's the introduction. This is how you obtain cumulants. What do they do for us now? So the first thing I want to point out that cumulants are what I call, I don't know if people call it like that, but I call it that. Cumulants are what I call statistically too many T's? No. Statistically irreducible. Irreducible. Okay. I don't know if other people call it like that, but here you go. I call it like that. So what it means that it's statistically irreducible. Let me try to explain it with an example. Why are you using this example? Okay, let's consider an example. So let's say that we have a process f of t that's actually a composite process. It's made out of process A and B, just a sum of two guys. But A and B are independent. Statistically independent, which means that independence means that if you take you take a moment of some mixture of A's and B's, right? And let's take a moment of those guys. Statistical independence means that the probability distributions factorize, which then translates that the moments factorize as well. Okay. So statistical independence means that this will break down into moment times moment. Um BU1 moment. That's statistical independence. Okay, now let's check out the Cumulant series for this process F made out of two independent processes. What happens here? So we take our coherence function, we put here AS plus BS TS, and we take an average. That's easy enough. And that guy, we can split the exponent into products of two exponents, right? These are numbers, we can do it. BS, TS, still average, whole product. Now, it won't be shocking to you if I say, because they are independent, so all the moments factorize, and I expand both X into a series, and I look at the moments, I factorize them, I will be able to reconstitute everything back into X, but the average will be factorized as well. SDS average times EI lambda 0T DS. All right, that's easy enough. All right. Let's see what I'm cooking here. Okay, but now we have a coherence function for A times coherence function for B. So we can just, they have their cumulant series expansions. So we can write it as n from 1 to infinity, I lambda n factorial with integral. We have cumulants of A. And we can do the same thing for B, for this guy, right? I lambda n factorial, integrals, u1. I'm running out of room for the cumulants here of B. Right? Or in other words, this is the e to high A of t times e to high B of t, right? Or in other words, it's high A t plus high B t, okay? So what is absent here? There is no high A plus B. There is no high A times B or something like that. They are independent, so there are no cumulants that would mix independent processes together, okay? There is nothing of the sort. We don't see anything like, I don't know, A, S, B, U. Nothing like that. We don't see them. Okay, and why we don't see them? Well, this is this is what I mean by statistical irreducibility, because you have already seen this, that cumulant is like, it's like a moment, but minus some corrections, like minus shortened moments, right? So if you check out this pattern for this process f which is equal a plus b. So if we take second cumulant for as S2 plus B S2 times A S1 plus B S1, take cumulant. Right, so this guy would be a second moment. No, let me write it like this. 2 A1 plus B1. Okay, so this is shorthand. A2 means A of S2. Okay. Moment minus A2 plus B2 average times A1 plus B1 average. Okay. New page. Let's continue here. And yeah, now we can collect some terms. So we can like multiply A2 times A1 here. So we'll get A2, A1 average. And here do the same. So we have minus A2 average times A1 average, all right? Same for B2 times B1 plus B2 times B1 average, and B2 times B1 here, or B average times B1 average, B2 average times B1 average. But we also have mixed terms, right? From both pieces. So we will have plus A2 B1 moment plus B2 A1 moment, and the mixtures here. So minus A2 B1 average minus B2 average times A1 average. Okay, that's sure enough, but A and B are, remember, independent. So this moment factorizes into product of averages. And this product of averages has its counter term here. So because of independence, this guy and this guy, they just cancel. And same with these guys, right? They also cancel. And this is just a second cumulant. Second cumulant, and this is also second cumulant of A. Second cumulant. All right? So what this shows, for me at least, is like cumulants, and you can check if you can inspect third cumulant, fourth cumulant, and so on. They have this funny looking pattern where you take a moment of some length and you like subtract all the possible like factorization of this moment into shorter moments. So, and these patterns, they play out in such a way that whenever anything under the longest moment would be independent, so that it would factorize, there will be counter terms that come in and just, kill what you get. Okay, so in this sense, cumulant is like a moment that got reduced by all the information available in all previous moments. Okay, so a cumulant is irreducible because cumulant is a moment reduced by everything that could be reduced by. All right. So in this sense, it's like a pure unique information. Cumulant of order n is just pure information that cannot be found in anything else. It's like unique in this way. In this sense, it's irreducible. You cannot, there is nothing you could reduce it by because everything what's in it is just, it's necessary. If you pull something out, it just unravels and disappears. So in this sense, it's irreducible. That's why cumulants are proper correlation functions, right? Because they just contain only unique information. You want something else, you go to lower order, cumulants or lower correlation functions. This whole hierarchy gives you a full picture of what's going on, but each individual piece is like pure irreducible information. In this sense, moments are easier to calculate, but they are trashed. I mean, not trashed, but they are each moment just carries with it the baggage of all the other moments that came before. It's just, just bursting in seams. Cumulants are nice and lean, efficient. Moments are bloated. This is the difference between them. And in fact, you can use this irreducibility to give an alternative definition for cumulants. So our original definition is this implicit thing, right? This implicit equation, which you have to expand and laboriously figure out what are the relations. But you can, once you realize this irreducibility, this pattern of these corrections that, you take a moment and chisel it of all the unnecessary stuff, you can write down formula for this pattern, but it's not pretty. Okay, that's why I never start with it. But once you are aware of what's going on, you can write it down and then explain what it means. So alternative definition, definition of cumulants. So this alternative definition embraces this idea that cumulant is a moment that's has been slimmed down by all the unnecessary stuff. Or in other words, a moment is some combination of cumulants, right? Because it goes both ways. If cumulants are the unique pieces of information, and moment is bloated, so a moment can be decomposed. Moment is reducible in the sense that it can be decomposed into some combination of cumulants, which are lean and efficient, right? And this decomposition can be written down in more or less explicit fashion. So you say the alternative definition is that you take a moment of order n and you say, okay, it equals to the following thing. You take a sum over p's partitions belonging to set part n to 1. I will explain it soon what it means, okay? So it's a sum over something. Then each term in a sum is a product over certain sequences. So I will use our tuple notation. So underline P underlined. So it is a tuple with k elements belonging to P. So this P, okay? So it is a product, and it's a product of cumulants. So you take P, K, S, P1, and the cumulant. So I'm explaining. Now I'm explaining. So like I told you, it's not a very pretty definition, but it's kind of explainable. So part, this is a set of ordered partitions of its arguments. So you get a set of n indices going from n to 1 or from 1 to n, whatever. and you partition it into sequences. Okay, so for example, part of 3 to 1. So that would be a set made out of, so the simplest partition is to no partition. So one sequence, okay? The other element, well, you can split it in two. For example, 3, 2, and 1. So we split it into a sequence of 2 elements and sequence of 1 element, which is still a sequence. And now you can see that, okay, so I can do some combination of this, of split into 2. So 3, 2, and 1, and now 3, 1, and 2. Another one will be 2, 1, and 3. So the partitions are ordered. Okay, so you don't switch. It's 3, 2, but not 2, 3. Okay, and the final term would be then just split it into 3 single element sequences. That's all possible partitions. All right. So P, capital P, is one of those splits. Okay. And small p, okay, is a tuple, and it contains elements numbered in this way. All right. So, for example, if I take this p, if I take p equal to 3, 2, and 1, so I will have here this guy would be p2 equal to 3, 2, right? So then p of 2 is 3. I mean, it sounds like nonsense, but mostly because it is kind of nonsensical. But this is like, you have to figure out this notation to cover it somehow. And the second option is you have just single element tuple, which is just 1, right? And then, so the first and last element is 1, okay? And this is how you index those cumulants, all right? So it's difficult to say, but you can check out some, play with it with examples on your own. I mean, if you take a first moment, so there is one element, there's no partitions, everything is simple, and you will get that first moment equals first cumulant. You take second moment, you have 2 elements, there are 2 possible partitions, you take 2, 1, or 2 and 1, and then you get a second cumulant plus product of first cumulants, which is what we see in here. Like, where is it? Right, second moment was here, second cumulant plus product of first cumulants, and so on and so forth. But it showcases this, that the moment is made out of irreducible parts. It's a combination of irreducible parts. Those irreducible parts are cumulants. So if you invert it, you get each cumulant can be expressed as some kind of combination of moments, combination such that, it's just, there are counter terms to cancel out things that are reducible in moments. So this is a story about cumulants. Hopefully I advertise them to you somehow, that say moments are for low IQ people. They are easy to calculate, so even a child can do it, but the real big brain, wrinkled brain people use cumulants because we know that they are irreducible, so they are like fancy, they are like smart and lean. Moments are bloated and stupid, right? So this is like a cumulants. But cumulants are fun and all, but I introduced them because we had a problem, right? There was a problem of not having dynamical equations. So how this whole story actually help us? Well, I like pointed at what would be the potential solution for our issue with dynamical equation. If moments had this fractal structure, they would factorize in some way, some pattern. Maybe we could like pull out the common factor, and then what's left would reconstitute into exponent again. Well, now we introduce cumulants. They actually gave us some factorization pattern, right? But more explicitly, we actually get our wish, because now, if I want to calculate the derivative of coherence function, so this is what we started with, right? This was the issue, and we couldn't find it. We weren't sure if we could find this coherence function on the right-hand side, but now we have our cumulant series expansion of t, right? Well, it's just exponent of some function of t. So you can just dot it, right? And by its very definition, the exponent have to reconstitute itself on the right-hand side, right? So what this means, that we have phi dot, times a lambda. So through this trickery, we kind of forced the issue, right? We forced the dynamical equation in a sense. However, we are not there yet, okay? Because we just renamed some stuff. It's impossible that it actually solved the problem for us, just renaming stuff, right? What's going on here then? Well, this series, cumulant series, even if we calculate its derivative, which we formally can, we can write down its formal derivative. So it will be I lambda. There will be a first cumulant, which is the same as first moment, if you remember. And then we have the rest of the series from 1 to infinity, I lambda n plus 1, n factorial. We have integral Sn ds1, ft, fsn, fs1.
Why n plus 1?
Give me a sec. And the W, no, I lambda 0 t. Yes. 1 second. I'm explaining everything. Okay. Why, cumulant series, again, I don't want to write it all the time, but just to recall, cumulant series, where was it? You see, okay, so it's each term in the series is a n-fold integral, right? Now you come here with derivative. So what you do is just cut out one of the, one of the f's under the cumulant average turns into f of t, and you lose one of the integrals. So effectively you get like, you can now, shift your n. You can shift to the dummy variable n, right? And when you do that, you get like extra power of lambda. because factorial disappears because this is like an ordered integration. So if you change it into ordered integrals, there wouldn't be a factorial here anyway. So that's why. So in other words, we did some trickery. We formally got our dynamical equation. However, this is only a formal expression because unless you can actually calculate explicitly what this series is or its derivative is, you cannot solve this dynamical equation. You cannot integrate it in computer unless high dot is a number, right? Is a function that can actually be explicitly written down. So it's clear that unless we do something with this series to make it, approximate it in some way, to make it a explicit expression, this is just a formal transformation of the dynamical equation of the derivative. So it's already good, because we by definition we get something that looks like has a form of dynamical equation. Now we know where to focus our attention. Okay, we know that we have to focus on this series, approximate it in some way, so that it has an explicit form, explicit expression, which can be plugged into our code and integrate the dynamical equation and be happy. And of course, the simplest approximation we can do here is to simply cut the series on some finite order, right? If you recall, we talked about when we talk about computability of unitary maps, right? I was like saying, okay, you could time-ordered exponent has this series representation as well, but when you cut it on some finite order, I said this is bad idea. This is very bad idea. So here I'm like trying to convince you that you have another series and we will cut it, and this is a good idea. But the difference is that this series, this high, it sits in exponent. So it's not just brainless cutting of some Taylor expansion at some order, which is bad, almost always bad. Here you're doing it in a fancy way. You cut a series, but then you plug it into exponent, which is already there's a lot of non-trivial stuff is going on. We expanded the exponent of a series previously, right? You see it here? I cut this series, I still have a lot of very complicated connections between the terms. It's not like cutting this series on the second order. It's completely different stuff. The accuracy, the preservation of some properties is much more powerful, better controlled. In fact, you could say, you probably heard about Feynman diagrams, right? Where you write down some diagrams and you construct the perturbation theories so you have some diagrams, but you cut them on some order. Those diagrams are cumulants in the end. Feel theoretical cumulants, but they are analogous to what we are talking about here. So each diagram is like a pictorial representation of a cumulant of a corresponding order, and by cutting the series of those diagrams on some finite order, you are cutting the cumulant series effectively, which then you plug back into some exponent. Of course, it's more fancy than what we are doing here because it's like field theory, but the idea is very similar. It's an analogous idea, okay? And we know that this is a powerful perturbation technique. So cutting cumulant series is I'm trying to cover my bases. It's a good idea. This is a good kind of idea. And indeed, if you, for example, do the simplest possible thing, so you cut on, let's say, second order. So let's let's cut high f on second order. So if we cut it on second order, we'll get W of t equals, how did I write it? I write it like this. Lambda f t bar, so the average, first cumulant, minus lambda square integral ft fs ds second cumulant wt wtf. Yeah, I should have f somewhere here, so wtf. Okay, I didn't thought about that. And so, this stuff, average, it's something you can calculate. If you know the correlation function, this is just a thing. You can calculate this. So this is a known function of time. You can integrate it. You can solve this equation. As a matter of fact, we could simply cut the series inside the x, right? And not bother with integration, but the point stays, right? We can just plug it in. Right, and the approximation, and because we are cutting the series. Right, so this is the solution of this equation, by the way. But the equation came from differentiating this exponent, so we are cutting high. Well, you can just cut it here in the exponent to begin with, but the point stays that we have forced dynamical equation in a place where it weren't before by considering cumulant expansion. This is a powerful technique which will carry on to the very end. So have like 10 more minutes left. Oh, and by the way, this is actually cutting high on some finite order. It does introduce this factorial like pattern. And you can see it explicitly, but by inspecting this formula here. So if I cut cumulant series on finite order, this means I'm setting all the cumulants of this order and higher to 0. Okay, so I cut on second order. That means that cumulants of order 3 and onwards are 0. So the only non-zero are second and first order. So and you inspect this kind of formula. So the only non-zero contributions would be some products of second order cumulants and average, right? So everything will be just a sum of factorized contributions, right? So this is why, and this particular pattern of this particular decomposition is actually key, because this is like fine-tuned to give you a factorization that once you factor out common factor, you are reconstituting exponents. Okay, which is key if you think about dynamical equations, where all the solutions will be some kind of exponent of something, ordered, time ordered, or otherwise. So that's the basic premise here. And this is a pretty good place to kind of stop. I will make one more very short remark, just a primer for the next week lecture. There is an interesting thing about cutting the cumulant series, okay? Because it's like at this point it seems like okay, I can cut it on some order. I determine which order I cut probably by examining. Maybe the cumulants are getting smaller and smaller, right? So I will get better and better approximation. If I let's say cut on fourth order would be a better approximation than cutting on second order because I have more terms, something like this. However, there is a tiny wrinkle here because there's a theorem, a very powerful mathematical theorem, which states that if the cumulant series is to represent a real stochastic process, it has to either have only two terms, so it would be cut on the second order, or it had infinitely many terms, infinitely many non-zero terms. It's called Marcinkiewicz theorem, and it means that the real stochastic processes has either two cumulants at most, or infinitely many non-zero cumulants. So it means that you can think that, oh, right, so this means that I cut either on second, or I cut or never cut the series, or I'm doing something that mathematics tells me it's incorrect. However, this is like you still can cut it on some k order, not necessarily two, because if a cumulant series is, let's say, non-physical in the sense that it violates this Marcinkiewicz theorem, where this means that W, the coherence function, would probably exhibit some kind of aberrant behavior. Let's say it would get larger than one at some point. That would be unphysical. However, if your cumulant series maybe have finite number of terms, larger than two, but it's still a good approximation of the whole series, the W that you get as a result aberrant behavior will be to the same approximation as your cut series, okay? So as long as it's the error does not explode, everything is fine. You can say, I'm satisfying Marcinkiewicz theorem with accuracy epsilon, okay? And it's all fine because theorems are binary. You satisfy or not, but if you introduce I satisfy with certain accuracy, you're good to go, okay? But this also shows that there's something special about processes that have two cumulants versus infinitely many cumulants. Those are called Gaussian processes, and we'll talk about them next week. So that's it.